Hello, everyone. Welcome to our presentation about OpenDSU's innovative technical ideas. We're excited to introduce the Data Sharing Unit, DSU concept, which we believe is as fundamental as familiar concepts like files, zip archives, or remote procedure calls, RPC. Often it takes time for new ideas to become widely known, especially if they don't come from major companies promoting them, but from academic research projects. You might be hearing about DSUs for the first time today, and we hope it becomes a valuable addition to your toolkit in building applications with heavy data sharing, with or without blockchains. The DSU concept is closely linked with the KeySSI concept. Imagine a KeySSI as both an identifier and a way to access the DSU, similar to how a file has a name and content. By controlling the KeySSI, you gain access to the DSU's contents, which can be a collection of files, much like in a compressed archive or a lightweight file system. OpenDSU simplifies this process for developers. One of its key features is the Blockchain Domain Naming System, BDNS, which allows DSUs to be anchored or referenced in a blockchain or distributed ledger. With the capability to use multiple ledgers, OpenDSU paves the way for truly decentralized data sharing. We'll explore more of this exciting world during our presentation. Using data sharing units, DSUs, changes how businesses work together, especially when security is really important. We're moving away from old methods to a new way using something called KeySSI. These KeySSIs let us control and manage DSUs at different levels of access. Nowadays, most businesses use APIs, which rely a lot on something called remote procedure calls, RPC. But DSUs work differently. With DSUs, we use what's called asynchronous messages instead of RPC. Different parts of a business or different businesses can share a KeySSI. They can work together in a process that's either managed centrally, like orchestration, or split among different groups, like in choreographies. Anyone who has the KeySSI can add to the business process whenever they want. They can put in new information, change stuff, and keep it all in the DSUs. In a way, DSUs are like a new kind of smart contract. They're like contracts that aren't directly on the blockchain, off-chain, or are on a secondary layer, layer 2. The main blockchain, on-chain, keeps track of the contract's overall state, but the detailed data is kept off the blockchain. The big goal of OpenDSU in using blockchain is to make things scale better, work faster, and be more private. Let's simplify and clarify what OpenDSU and its main component, the DSU, Data Sharing Unit, are all about. In business blockchains where many companies are involved, sharing data is a big challenge. Storing all this data directly on the blockchain isn't a good idea because it can be slow and not private enough. That's where DSUs come in as a smart solution. DSUs offer a different way to handle data. They use well-known security methods like symmetric encryption and private key signatures. This means they can safely store data off the main blockchain, that's called off-chain, but still keep a basic record on the blockchain for verification. This method is efficient and keeps data private. It's a bit like zero-knowledge proofs, ZKP, but simpler and without needing complex new cryptography. Each DSU has its own unique key for security. This key not only protects the data, but also helps manage who can see or change it. You can think of a DSU as a secure box where you can store files or even some code. We'll talk more about how these boxes are efficiently organized later. For developers, working with a DSU is like using a very lightweight version of a Docker container. But instead of running programs, it's mainly for storing and sharing data. You can even mount a DSU inside another DSU, like mounting file systems on Unix. These DSUs can be set to either just be viewed, read-only, or to allow changes, write mode. They can also act like tiny databases or ledgers, keeping track of transactions based on DSU's blockchain anchoring. In simple terms, think of a DSU as a special kind of folder or file container that you can easily share using a key. This key not only helps in finding the actual storage of the encrypted container on the network, but also controls access to it. A system using data sharing units, DSUs, needs to carefully consider the different types of DSUs it will use, essentially acting as data models. Each DSU type defines what kind of data it can store. It's also possible to include code within a DSU, although this is less common due to the security risks associated with mobile code. Nevertheless, there are effective applications for this. such as digital wallets storing encryption keys or in the use of DSUs for microledgers, which are basically off-chain smart contracts. These contracts regulate who can update the DSU's state and in what manner, serving as off-chain smart contracts that are shared within a small group of an enterprise entities or potentially with a wider public audience. To summarize, data sharing units, DSUs, are secured and identified through keys. They have the capacity to store keys that are essential for encryption and digital signatures. DSUs can handle various types of data, functioning as file systems or embedded databases, including key value stores, index databases, or ledgers. They can also contain code that is crucial for validation and implementing business logic, a feature that is specific to each DSU type. These DSU types, also referred to as DSU constitutions, resemble classes in traditional programming, defining the structure and capabilities of each DSU instance. Additionally, DSU APIs serve as abstract interfaces, concealing the internal representations of data. We should note that in most cases, DSUs are used for sharing data and are not generally viewed as abstract containers for code or as providers of APIs. However, as adoption increases, we believe new perspectives on the fundamental concept of DSUs, and additionally the idea of DSU types, will emerge. Besides the DSU and KeySSI concepts, which we'll delve into shortly, let's begin with understanding BDNS, which stands for Blockchain Domain Naming System. The main function of BDNS is to convert meaningful human names into configurations for blockchain networks. In simple terms, just as DNS maps domain names to IP addresses, BDNS maps blockchain names to configurations. These configurations are typically endpoints for services needed to access OpenDSU subsystems. Today, we'll discuss subsystems like anchoring, bricking, and DID-based message queues. BDNS is essentially the DNS for OpenDSUs and could potentially even replace the traditional DNS system established in 1985. It's designed to be a hierarchical and decentralized naming system, not only for blockchains and distributed ledgers, but also for individual DSUs, which are like the endpoints of this hierarchical structure. BDNS is an extension or complement to DNS, maintaining the familiar user experience for the average person. Examples of blockchain domains could include addresses like vault.company.pharmaledger or epi.company. The domain names used in BDNS, Blockchain Domain Naming System, are essentially just strings. The ultimate goal is to develop a global resolver similar to DNS. However, for now, OpenDSU is primarily used in enterprise scenarios like those of the PharmaLedger Association, and a global system isn't yet necessary. In summary, BDNS enables the use of multiple blockchains or ledgers within a solution, achieving decentralization by segregating where data is anchored and stored. It's feasible to use the same physical blockchain and divide it into multiple subdomains. This approach allows for the reuse of the same blockchain infrastructure across various use cases or for enhanced security. From the perspective of off-chain data storage, BDNS domain names provide public configurations for endpoints that can serve off-chain data, which we will discuss later as the encrypted bricks concept. In terms of infrastructure for communication through messages in a decentralized environment, BDNS names facilitate the implementation of W3C DID methods. These methods use BDNS domains in their identifiers, enabling the creation of DID methods that don't rely on centralized resolvers. This approach offers the advantages of methods like WebDID, but decentralized and properly using distributed ledger technologies to improve security and trust. In the diagram, we aim to give an understanding of how BDNS domains assist in dividing various subsystems into two main categories: confidential data storage or off-chain storage, and multiple blockchains, on-chain. We highlight 4 DSUs anchored in 4 different subdomains, yet they might still be a part of the same blockchain enterprise use case. We also point out an optional component, the root ledger, located in a different subdomain. This root ledger could facilitate something like blockchain anchoring, which is used to enhance security between different blockchains. Additionally, the diagram showcases the most common form of anchoring we employ, known as hash-link anchoring. This method connects the DSUs with various ledgers or blockchains. As previously mentioned, the 2024 implementation of OpenDSU does not mandate a global root for BDNS, making its inclusion optional. It is showcased primarily to convey the comprehensive vision of the technology. It's important to understand the OpenDSU vision for widespread adoption, which envisions the next stage of a more secure internet. This future internet could comprise thousands, if not millions, of blockchains or ledgers. BDNS would be instrumental in enhancing the traceability and security of data sharing across a wide range of potential use cases. In this scenario, BDNS could take on a central role in organizing these parallel blockchain networks, facilitating easy data sharing and trust transfer. We have reached a point where we can discuss the central mechanism of how DSUs operate. In this diagram, we highlight three key conceptual elements: a runtime environment for business applications, also known as the DSU reconstruction environment, a blockchain component for on-chain storage of DSU anchors, and an off-chain data storage component in the form of bricks. Bricks can be thought of as encrypted data, which are referenced by a digital fingerprint, known as a hash or hash link, and cannot be used without the corresponding decryption key. This makes them safe to expose on the internet without significant security risks. The idea is that their identification is a number generated based on the content and encryption keys, making it difficult to differentiate between different hashes without information from the anchoring system. This is where anchoring in a ledger or blockchain comes in, allowing for the identification of relevant bricks. These bricks are then downloaded within applications, which can be digital wallets or even classic APIs. OpenDSU is an SDK that can be integrated on both the server side and the client side. In summary, blockchain is used for anchoring, with an approach to minimize data leakages and maximize decentralization. This is achieved by using client-side encryption, even when the DSUs are reconstructed on servers, as those servers will require access to the appropriate KeySSI. Typically, the DSUs are reconstructed in a sandbox environment, which could be cloud or edge agents. A KeySSI serves a dual purpose. It is both an access token, a key, and an identifier. The term KeySSI stands for Key Self-Sovereign Identifiers. It plays a crucial role in connecting to DSUs, as it helps in identifying and locating them, functioning much like a URI. Additionally, KeySSI is utilized for the encryption of DSUs, facilitating decentralized access control. Beyond encryption, KeySSI is essential for validating DSUs and proving ownership. It also manages the identity and control of the DSU's anchors, particularly in the context of blockchain anchors that require zero access. Furthermore, KeySSI can be employed to implement DID, decentralized identifier methods. These DID methods adhere to the specific decentralized access control rules set by OpenDSU, ensuring a secure and autonomous digital identity framework. In the structure of a self-sovereign identifier, SSI, each part plays a specific role. 1. The first part, indicated by SSI, confirms that the key is a self-sovereign identifier. 2. The second part, labeled as type, specifies the complementary types of KeySSI, categorizing its specific function or use. There are many types, the most common being seed, SRED, ZA, as we will explain later. 3. The third part, ledger domain, is crucial as it denotes the BDNS domain for a ledger or blockchain. This part identifies which specific blockchain or ledger the KeySSI is associated with. 4. Following this, the fourth part consists of type-specific substrings. These substrings are essential for security, containing a significant number of random bits to ensure the KeySSI's uniqueness and security. 5. The fifth part, known as the control substring, is used by anchoring services. It plays a critical role in validating requests for updating the version of the anchored DSU. The algorithm employed for this verification varies depending on the KeySSI type, usually as a public key. 6. The sixth part, VN, stands for the version number of the KeySSI type. It's important to differentiate this from the number of versions of DSUs, as each DSU instance could have multiple versions. This number is more a version of the protocol. 7. Finally, the seventh part, hint, is an optional component that provides subtype-specific information, further detailing the KeySSI. To illustrate these parts, consider these examples. In SI seed, default 7p v0, each section from SSI to v0 corresponds to the parts mentioned above. Similarly, SSI ZA, default E064 F097 F6 v0, follows the same structural pattern, with each segment representing a specific aspect of the KeySSI. The most commonly used KeySSI belong to the seed SSI family of OpenDSU keys. The seed SSI functions similarly to a seed phrase used in Bitcoin wallets and essentially consists of a BDNS domain and a random number. It provides write access to the anchored DSU. Typically, a seed SSI is not shared by their owner. However, for sharing purposes, an sRead key can be derived from a seed SSI. The sRead SI offers read access to the anchored DSU. The DSU is encrypted with a symmetric key that is derived from the sRead SSI. The SZA SSI, on the other hand, provides zero access. Possessing an SZA SSI implies the existence of a corresponding seed SI and indicates that the attached DSU has a certain number of versions. The hashlink SSI is utilized for storing the hash of the DSU's bricks in blockchain. To understand all the cryptography and logic used to derive these keys, it is recommended to read the OpenDSU docs. In essence, an SZA is a key that identifies the DSU on the blockchain and is stored along with the hashlink SSI in the form of anchors. Both the seed SSI and the sRead SSI are kept in wallets or key management systems and are never stored on the blockchain, as they provide write or read access to the DSUs, respectively. The sRead SSI is used to read the data and also can verify that it was signed by someone who controls the seed SSI of the DSU. Now we can try to piece together all these elements step by step. The data stored in DSUs undergoes a number of updates, with each update creating a new version of the DSU. Typically, these updates are managed under the control of a wallet, though not necessarily the same wallet, especially in cases where DSUs are shared among multiple entities with write permissions. The data is transformed into bricks, a process often referred to as bricking or brickification, and the digital fingerprint of the data from these bricks is anchored in the blockchain. In fact, we can delve into more detail about this process using this diagram. We see how a seed SSI is used to derive an sRead SSI, and from this sRead SSI, an anchor ID is derived. Attached to this anchor ID are multiple hash links that are stored in the blockchain. In an external system called brick storage, data is encrypted and stored in the form of bricks, which can be identified by hash links. We begin to distinguish two types of bricks: normal bricks that contain data from the files in DSUs, and brick maps, which function like a map system holding organizational information of the content, somewhat similar to a file allocation table in a FAT file system. These brick maps also include a unique, random encryption key for each brick. A file stored in a DSU may consist of one or multiple bricks. Smaller files might have just one brick, while larger files could be made up of several. Between different versions of DSUs, files that don't change will have the same bricks, leading to storage efficiency. New bricks are created only when there is new data. However, new brick maps are created for each version since we are dealing with a structure akin to a Merkle tree. Therefore, any change in a file will inevitably cause changes in the content of brick maps. Here, we explain the role of brick storage, which is essentially a web service dedicated to storing and retrieving bricks. Once a brick is created, it becomes read-only and is identified by a hash. In this system, a DSU is saved as a collection of bricks. This saving process begins with a brick map, which acts as a reference point, linking to all other bricks that comprise the DSU. When there's a need to load a DSU, the OpenDSU SDK initially loads the first brick, the brick map. Then, when a file is required, it proceeds to load the rest of the bricks that make up the DSU based on the information in the brick map. This loading is done in a lazy manner, meaning on demand, allowing for efficient loading of the DSU in various situations. In this diagram, we summarize what we have discussed, clarifying that an anchor identified by an anchor ID that typically consists is an SA key SSI. While other types of anchors are possible, they are beyond the scope of this current presentation. These anchors contain a list of hash links, which are chained and signed with a private key derived from the seed SSI, or generally with the key that allows writing to the DSUs. These hash links point towards the brick storage system, specifically to the brick maps of each version of the DSUs. We hope that from this explanation, the main idea and the operational method of DSUs are now clear. Please take a pause and stop the video to think about it if it's still not clear. In the next slides, We will just present some details about the implementation and a conclusion. In this slide, we begin to introduce the architecture of OpenDSU. However, this is merely an overview. For a deeper understanding and to start using OpenDSU in real projects, we recommend visiting the OpenDSU.com website or contacting Axiologic for training or consultancy. The architecture of OpenDSU is layered, designed to be blockchain agnostic, meaning it can utilize any blockchain system. This flexibility ensures integrity and traceability in the data. The concept of hierarchical blockchains is employed to increase security, recognizing that no single solution fits all needs. A key feature of OpenDSU is the emphasis on off-chain data and computation integrity. This approach extends to the use of off-chain smart contracts, allowing for a use case-specific model. Each layer and component of OpenDSU is crafted to provide robust, flexible solutions tailored to specific project requirements. The OpenDSU architecture, designed with microservices, is flexible and well-suited for a wide range of applications. It especially supports enterprise wallets for secure key storage, and we have extensive experience in implementing integrations with existing enterprise systems. OpenDSU offers a variety of APIs that are adaptable and customizable for distinct use cases. Our core microservices include anchoring APIs and bricking APIs, both of which can be efficiently sharded by BDNS, enhancing the system's reliability. For the secure processing of data, we utilize cloud enclaves. In terms of storage, OpenDSU not only covers traditional data storage, but also extends its capabilities through cloud enclaves. This integration includes proper key management systems, ensuring enhanced security and effective management of cryptographic keys. We've come to the end of this presentation, tailored for programmers and architects. For further insights, I encourage you to visit our YouTube channel, where we have additional presentations designed for business professionals and architects. These videos provide more detailed information on specific aspects of OpenDSU. The aim of this concluding slide is to highlight the advantages of OpenDSU compared to using traditional transaction managers. DSUs, in combination with wallets that can also be implemented using DSUs, can be envisioned as a new kind of blockchain-agnostic private transaction managers. Let's summarize the key benefits of OpenDSU. OpenDSU ensures confidentiality for both enterprises and individuals, a crucial aspect in today's digital world. OpenDSU introduces new concepts like DSUs and KeySSIs, significantly simplifying programmability. OpenDSU aims to standardize the off-chain layer and key management, promoting data portability in a blockchain-agnostic manner. OpenDSU can reduce or even eliminate access to confidential data for service providers, adhering to the principles of data minimization. OpenDSU opens up scalability opportunities by reducing the blockchain to its core roles, such as timestamping and events ordering. Traditional transaction managers, in comparison, are seen as partial solutions. They can be complex and only partially address confidentiality issues. There's also the challenge of incompatible data formats between different blockchains, like Hyperledger Fabric and Quorum. Privacy becomes a concern, especially in SaaS models or when dealing with personal data, like patient information. In such cases, hosting servers transform into powerful intermediaries and privacy is compromised. In contrast, DSUs offer an elegant way to segregate data while maximizing the security of data sharing, addressing significant scalability and interoperability challenges that are inherent in database-centric alternatives. In wrapping up, I'd like to express my enthusiasm for our collective journey into decentralized technologies. For a comprehensive understanding of our open-source project and detailed documentation on OpenDSU, you can visit www.opendsu.com. Our codebase is open for exploration and contributions on GitHub at github.com/OpenDSU. To fully grasp the vision and drive behind OpenDSU, Axiologic is here to assist you in using DSUs. You can contact us at axiologic.net. Your participation and contributions are crucial in shaping the future we are building together. Don't forget to follow our channel and our GitHub repositories. Thank you.